The morning of March 19th, 1942, broke grey and heavy over the coastal waters near New Guinea. Lieutenant Commander Takeo Shibata stood in the wreckage of what had been an American B-25 Mitchell bomber, his boots crunching on shattered plexiglas and torn aluminum. The aircraft had crashed during a low-level attack on Japanese positions 2 days earlier, its crew killed instantly when the bomber cartwheeled across the jungle clearing. But Shibata wasn't interested in the dead. He was interested in what they'd left behind. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Carefully mounted in the bombardier's station, still intact despite the violence of the crash, sat a device unlike anything Japanese engineers had seen before. Roughly 50 pounds of intricate machinery, 2,000 precisely joined parts including gyroscopes, motors, gears, mirrors, and levers. An analog computer that promised to solve one of modern warfare's most vexing problems, dropping bombs accurately from high-altitude aircraft traveling at high speeds. The Norden Bombsight, America's most closely guarded secret, now sitting in Japanese hands. Shibata had spent 12 years as a precision instrument designer for Mitsubishi Heavy Industries before the war. He understood complexity, mechanical harmony, the delicate marriage of optics and motion. Japanese bomb aiming technology relied on modifications of outdated German designs from the previous war, simple vector calculators requiring extensive manual computation and offering marginal accuracy. The Americans, intelligence suggested, had created something revolutionary. The recovery team worked through the humid afternoon, cutting away twisted metal to extract the bombsight intact. They wrapped it in canvas salvaged from the bomber's torn fuselage, protecting it from moisture that would corrode the precision mechanisms. Within hours, the device was on a transport aircraft bound for Tokyo, accompanied by Shibata and a team of specialists who would spend the flight discussing what they might discover. Shibata had examined crashed American bombers before, studied their construction techniques, analyzed their engines and instruments, but never had he possessed a complete example of their legendary precision bombing system. American propaganda claimed bombardiers could hit a pickle barrel from 20,000 feet. Japanese intelligence dismissed this as exaggeration, wartime boasting designed to intimidate. Yet Allied bombing accuracy, when conditions permitted visual targeting, exceeded anything Japanese forces achieved. The journey to Tokyo took 5 days, the transport making multiple refueling stops at captured airfields across the Pacific. Shibata travelled in the cargo hold, unable to leave the precious cargo unattended. His mind raced with questions examined from every angle. How did the Americans achieve stabilization in 3 dimensions? What power source drove the complex mechanisms? Most critically, could Japanese industry replicate this technology? Tokyo in March 1942 remained untouched by American bombs. That would change dramatically just weeks later when Lieutenant Colonel Jimmy Doolittle's B-25 Seconds aircraft, identical to the one that provided Japan's intelligence windfall, would strike the capital in a daring, carrier-launched raid. But on this morning, the city bustled with the confidence of a nation whose military forces had conquered vast territories across Asia and the Pacific. The Imperial Japanese Army's Technical Research Institute occupied a sprawling complex in western Tokyo, its laboratories and workshops staffed by Japan's finest engineers and scientists. When the captured Norden arrived on March 24, 1942, a team of 40 specialists stood waiting. Major General Yasunori Takeuchi, the institute's director, walked slowly around the crated bomb site, his expression unreadable. Takeuchi had studied mechanical engineering at the Imperial University of Tokyo before joining the Army's Ordnance Department. He'd overseen development of Japan's Type 97 bombers, designing fire control systems and improving bombing accuracy through incremental refinements to existing technology. He knew Japan's bombing capabilities lagged behind American and German standards. Perhaps this captured American device would reveal methods for closing that gap. Over the next week, Takeuchi's team would photograph every angle, document every component, and begin the careful process of disassembly. They would measure tolerances, analyze materials, and test each system. The findings would be forwarded directly to Prime Minister Hideki Tojo and the Supreme War Council, men desperately seeking technological advantages as Japan's defensive perimeter expanded to unsustainable dimensions. No one present that spring morning could have predicted what they would discover, nor how the revelation would illuminate fundamental differences between American and Japanese industrial philosophies that would ultimately help determine the war's outcome. The initial examination began on March 25, 1942, under harsh electric lights that transformed the laboratory into a theater of revelation. Shibata led the mechanical analysis team, while Takeuchi supervised structural evaluation. A third group, led by Captain Hiroshi Nakamura, a specialist in optical instruments from Nippon Kogaku, would evaluate the bombsight's vision systems. 3 perspectives, 1 goal: understand how America was achieving unprecedented bombing accuracy. Nakamura approached the bombsight first, carefully examining the sighting telescope. The optical quality struck him immediately. American lens manufacturing had achieved remarkable clarity, using techniques Japanese industry struggled to replicate. The telescope provided magnification and precision that Japanese bomb aimers could only envy. "Gentlemen," he called to his team, "examine the lens coatings. This is not standard optical glass. The Americans have developed anti-reflective treatments we've only theorized about." He measured the telescope's focal length, calculated field of view, and noted the ingenious integration with the device's mechanical computer. German optics, particularly Zeiss instruments, had long dominated precision applications. These American lenses matched or exceeded German standards. The integration fascinated him most. Japanese bombsights separated optical and computational elements, requiring bombardiers to manually transfer data between systems. The Norden unified everything into a single, coherent mechanism. Pilot's problem of maintaining constant heading and altitude had been solved through direct connection to the aircraft's autopilot, a feature Japanese bombers entirely lacked. Takeuchi's structural team photographed the bombsight from every conceivable angle, creating detailed documentation for analysis and potential replication. The device measured roughly 2 feet tall by 18 inches wide, dominated by a large gyroscope housing on the left side and the mechanical calculator with sighting head on the right. The construction revealed American manufacturing philosophy that differed dramatically from Japanese practices. Japanese precision instruments emphasized craftsmanship, individual components carefully fitted by skilled technicians. The Norden showed evidence of mass production, standardized parts manufactured to consistent specifications, allowing rapid assembly. This wasn't artisanal work. This was industrial engineering on a scale Japan's workshops couldn't approach. This device was not hand-built by master craftsmen, Takeuchi observed during the first evening's briefing. It was produced in a factory, probably by semi-skilled workers following standardized procedures. Yet the precision exceeds our best hand-fitted instruments. The Americans have achieved what we believed impossible: mass-produced perfection. Shibata spent 3 days examining the bombsight's gyroscope stabilization system. The American gyroscope spun at approximately 7,200 revolutions per minute, maintaining a stable platform that compensated for aircraft motion in all 3 axes. Japanese gyroscopes, primitive by comparison, struggled with single-axis stabilization. The power system proved equally sophisticated. The Norden operated on 24-volt electrical power provided by the aircraft's generators, with backup capability from onboard batteries. Japanese bombers used 12-volt systems, inadequate for powering complex instruments. Upgrading entire aircraft electrical architectures would be required to support Norden-style equipment. Each discovery led to more questions. The mechanical computer continuously recalculated bomb trajectory based on airspeed, altitude, wind conditions, and bomb ballistics. It performed calculations that would take a trained bombardier several minutes in mere seconds, automatically adjusting for changing conditions during the bombing run. "How many components?" Shibata asked his assistant, a young engineer named Kenji Yamamoto, fresh from Technical University. Yamamoto consulted his documentation. Preliminary count suggests over 2,000 individual parts: major, gears, bearings, springs, levers, mirrors, electrical contacts. The precision required for manufacture is extraordinary. He measured several gear teeth under magnification. Tolerances are impossibly tight. These gears mesh with clearances measuring hundredths of millimeters. Our best manufacturing equipment cannot achieve this consistently. Shibata examined the gear assembly himself. Yamamoto's assessment was accurate. These components would never emerge from Japanese workshops without extensive retooling and development of new manufacturing techniques. The Americans possessed industrial capabilities Japan couldn't match, at least not quickly. The autopilot integration system revealed perhaps the most sophisticated engineering. The Stabilized Bombing Approach Equipment, or SBAE, connected the bombsight directly to the bomber's flight controls. During the final approach to target, the bombardier's Norden inputs automatically adjusted the aircraft's heading and attitude, flying the plane more precisely than any human pilot could manage manually. This automation reduced crew workload dramatically. The bombardier focused entirely on target acquisition and refinement of the bomb release point. The pilot monitored systems but relinquished fine control to the automatic systems. Japanese doctrine required pilots to manually fly precise courses, while bombardiers simultaneously calculated drop points, a task-saturated approach that degraded accuracy under combat stress. April 2, 1942, brought the first operational testing attempt. Takeuchi's team had studied the captured Norden extensively, photographed every component, measured every dimension. Now came the crucial question: could they make it work? The bombsight required careful initialization before use. The gyroscope stabilization platform needed righting, aligning its reference frame to true vertical. American technical manuals, partially translated by intelligence officers, described a time-consuming process comparing the platform's attitude to spirit levels, visible through windows on the stabilizer housing. This alignment could take 8 minutes under ideal conditions. Under laboratory conditions, the Japanese team required 40 minutes to achieve proper alignment. The process demanded precision that Japanese training hadn't emphasized. American bombardiers, according to captured training documents, practiced these procedures hundreds of times until they became second nature. Japanese bomb aimers received minimal instrument training, relying instead on experience and intuition. Once properly initialized, the Norden's capabilities became apparent. Shibata input test parameters: altitude of 5,000 meters, airspeed of 300 kilometers per hour, bomb weight of 250 kilograms. The mechanical computer hummed to life, gyroscopes spinning, gears meshing, calculating the theoretical bomb impact point based on ballistic tables built into the device. The precision was remarkable. The bombsight computed angles to 3 decimal places, adjusted for wind drift in real time, and indicated the precise moment for bomb release with mechanical authority. Japanese bombing calculations, performed manually using slide rules and reference tables, achieved perhaps 1 decimal place accuracy at best. "This is not a bombsight," Captain Nakamura said quietly, watching the device operate. "This is a complete bombing system. It replaces the bombardier's brain, the pilot's steady hand, and hours of training with mechanical precision." He paused, understanding the implications. "We cannot build this. Not now, perhaps not ever." The room fell silent. Takeuchi had reached the same conclusion but hoped one of his specialists might identify a path forward. Japan's precision manufacturing capabilities, while excellent by Asian standards, lagged years behind American industrial sophistication. The tolerances required, the materials specifications, the integration of optical, mechanical, and electrical systems, each challenge would require months or years of development. April 15, 1942. Lieutenant Colonel Doolittle's B-25 bombers struck Tokyo, shocking Japan's military leadership and demonstrating that the American mainland could reach the heart of the empire. Ironically, those raiders carried no Norden bombsights. The secret devices had been removed before the mission, replaced with simple $20 sights better suited to the low-altitude attack profile. But the psychological impact was profound. Americans could strike Japan, and when they returned in force with their heavy bombers, they would bring their precision bombing technology. The captured Norden suddenly represented not just a technical curiosity, but an urgent glimpse of the threat Japan would soon face. Takeuchi prepared his preliminary report, a document that would eventually run to 80 pages with detailed technical appendices. The report opened with stark assessment. The American Mark 15 Norden bombsight represents the most significant challenge to Imperial Japanese bombing doctrine, not through any single superior feature, but through systematic integration of multiple advanced technologies into a unified bombing solution. The report detailed every aspect of the examination: mechanical analysis, optical evaluation, electrical systems assessment, and operational implications. But Takeuchi structured it around three fundamental conclusions that would disturb anyone reading carefully. First, the Norden achieved unprecedented accuracy through automation rather than skill. American doctrine assumed average crews using sophisticated equipment would outperform elite crews using primitive equipment. Japan's doctrine emphasized the opposite: elite crews compensating for equipment limitations through superior training and dedication. American philosophy scaled, Japanese philosophy didn't. Second, the Norden's complexity required equally sophisticated support infrastructure. American industry could mass-produce 2,000-part precision instruments because American factories possessed machine tools, skilled workers, quality control systems, and supply chains that Japanese industry lacked. The device wasn't just technology, it was the manifestation of industrial capacity Japan couldn't replicate. Third, American bombardment doctrine was fundamentally different. Japan used bombers for tactical support of ground operations. Hitting close-range targets required modest precision. America planned strategic campaigns against distant industrial targets requiring pinpoint accuracy. The Norden was purpose-built for America's strategic vision, a vision Japan neither understood nor possessed the capability to counter effectively. Takeuchi included recommendations, though he knew they faced insurmountable obstacles. Japan should attempt to develop a simplified version incorporating Norden principles while accepting reduced capability. Priority should focus on improving existing bomb sites incrementally rather than attempting to match American standards. Most importantly, Japan needed realistic assessment of what its bombers could and couldn't accomplish against well-defended targets. The recommendations would be largely ignored. Japanese military culture resisted admitting enemy superiority or accepting technological limitations. The notion that Japanese ingenuity and fighting spirit couldn't overcome material disadvantages conflicted with fundamental assumptions about the war. May 7, 1942, marked the beginning of Japan's attempt to create a domestic version of the Norden bombsight. Despite Takeuchi's pessimistic assessment, orders came from the highest levels: reverse engineer the American device and equip Japanese bombers with equivalent capability. The project received designation Type 4 Automatic Bombing Site and priority allocation of scarce resources. Shibata was placed in charge of the development effort, a responsibility he accepted with deep misgivings. He had spent weeks studying the Norden, understanding not just how it worked but why certain design decisions had been made. The Americans had created this device in 1931, more than a decade of development, testing, and refinement. Japan hoped to replicate it in months. The development team established specifications for the Type 4, necessarily simplified from the original Norden. The gyroscope system would use available Japanese components, accepting reduced stabilization accuracy. The mechanical computer would calculate fewer variables, sacrificing precision for manufacturability. The optical system would use Japanese lenses, inferior to American coatings, but adequate for basic function. Early prototype work revealed the magnitude of the challenge. Japanese gear-cutting equipment couldn't achieve the tolerances required for smooth operation. The gyroscopes, even spinning at lower speeds, suffered from bearing quality issues causing precession errors. Electrical systems experienced reliability problems under vibration and temperature extremes common in bomber operations. Material shortages compounded technical difficulties. By mid-1942, American submarines were beginning to interdict Japanese supply routes, reducing availability of strategic materials. Chrome, nickel, molybdenum metals, essential for precision instruments, became increasingly scarce. Engineers substituted inferior materials, degrading performance further. Manufacturing capacity presented the ultimate constraint. Even if technical problems could be solved, Japanese industry lacked the machine tools and skilled workers to mass-produce complex bomb sites. The Norden Company in America operated multiple large facilities, employing thousands of workers, producing hundreds of bomb sites monthly. Japan's entire precision instrument industry was smaller than a single American Norden factory. Shibata wrote in his private journal, "Never meant for official reports. We have been asked to replicate in months what required America a decade, using tools and materials inferior to those available to our enemy, with workers less trained and factories less equipped. The task is impossible, yet we cannot admit this truth." By September 1942, the Type 4 project had produced 3 prototype bomb sites. Testing revealed performance dramatically inferior to the captured Norden. Accuracy was poor, reliability questionable, and operational complexity excessive. The devices required constant maintenance by specialized technicians, defeating the purpose of standardized equipment. Takeuchi's report to the Supreme War Council was diplomatically phrased but honest in its conclusions. The Type 4 automatic bombing sight incorporates principles learned from examination of captured American equipment. However, manufacturing limitations and material constraints prevent achievement of comparable performance. Further development is not recommended given current resource priorities. The report suggested abandoning attempts to match American bombing technology. Instead, Japan should focus resources on areas where it could compete effectively: pilot training, tactical doctrine, and defensive systems to counter American strategic bombing. The recommendations were partially implemented, though politically, complete abandonment of the Type 4 project proved impossible. December 1942 brought a second iteration, designated Type 1 Model 2 automatic bombing sight. This design simplified even further, eliminating features that Japanese manufacturing couldn't support. The result was a device that bore superficial resemblance to the Norden but functioned more like an improved version of Japan's existing bomb sights. Production began in early 1943, but output remained minimal. By war's end, fewer than 20 Type 1 Model 2 bomb sights had entered service, equipping a handful of elite bomber units. The devices provided marginal improvement over standard equipment, but nothing approaching the capabilities Shibata had observed in the original Norden. The captured American bomb sight remained at the Technical Research Institute throughout the war, a monument to industrial capabilities Japan couldn't achieve. Engineers would occasionally visit to study specific systems, seeking insights for other projects. But the device primarily served as a sobering reminder of American technological superiority. As we reach the midpoint of this story, if you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The strategic implications of the Norden evaluation extended far beyond technical specifications. By early 1943, American B-17 Flying Fortresses and B-24 Liberators were conducting daylight precision bombing raids over Europe with devastating effect. Intelligence reports reaching Tokyo described formations of hundreds of bombers, each equipped with Norden bomb sights, systematically dismantling German industrial capacity. Japan's military planners understood what this portended. American heavy bombers would eventually reach Japanese home islands, bringing the same precision destruction currently ravaging Germany. Without equivalent bombing technology or effective countermeasures, Japan faced systematic demolition of its war-making capability. Captain Hiroshi Nakamura, the optical specialist who had first examined the captured Norden, was tasked with a different kind of analysis in March 1943. Rather than studying the device itself, he was to evaluate American bombardier training programs based on captured documents and prisoner interrogations. What he discovered was as illuminating as the hardware examination. American bombardier training consumed 6 months, involving hundreds of hours of classroom instruction, simulator practice, and live bombing exercises. Trainees learned not just how to operate the Norden, but how to maintain it, troubleshoot malfunctions, and extract maximum performance under combat conditions. The training investment per bombardier exceeded $50,000 in 1943 currency, a staggering sum reflecting American commitment to precision bombing doctrine. Japanese bombardier training, by comparison, lasted 6 weeks and focused primarily on manual calculation methods and basic instrument operation. The training investment per bombardier was perhaps 1/10 the American equivalent. Japan simply couldn't afford the time, resources, or specialized instructors required for American-style training programs. But the contrast went deeper than training duration. American doctrine treated bombardiers as specialists, highly trained technical operators whose sole responsibility was accurate bomb delivery. Japanese doctrine expected bombardiers to perform multiple roles: navigation assistance, defensive gunnery, even aircraft maintenance. The divided attention inevitably degraded bombing accuracy. Nakamura's report emphasized this systematic difference. American bombing effectiveness stems not merely from superior equipment, but from a comprehensive system encompassing advanced technology, extensive training, specialized roles, and realistic doctrine. Japan has attempted to replicate the technology while ignoring the supporting system. This approach cannot succeed. The analysis reached General Takeuchi's desk in April 1943, alongside increasingly grim reports from the Pacific Theater. American forces were advancing steadily, island by island, airfield by airfield, bringing their heavy bombers ever closer to Japan. The captured Norden bombsight, once a curiosity, now represented an existential threat. Takeuchi called a meeting of senior engineers and military officers to discuss strategic implications. The gathering, held in a secure conference room beneath the Technical Research Institute, brought together Japan's finest technical minds to confront uncomfortable truths. "Gentlemen," Takeuchi began, "we have spent a year examining American bombing technology. We understand how it works, and why we cannot replicate it. The question now is what this means for Japan's defense." Lieutenant Commander Shibata presented the technical summary. The Norden bombsight represented approximately 15 years of American development, from Carl Norden's initial prototypes in the 1920s, through continuous refinement into the Mark 15 model, captured in 1942. The development program had cost over $1 billion, employing thousands of engineers and consuming resources that simply didn't exist in Japan's economy. The Americans spent half the cost of their atomic bomb program on bombsight development, Shibata noted. This investment reflects their strategic commitment to precision bombing. We cannot match this commitment, nor do we possess the industrial infrastructure such an effort would require. Production statistics illustrated the disparity. By 1943, American factories were producing over 1,000 Norden bombsights monthly. Each device contained 2,000 precisely manufactured components, yet production had been systematized to the point where semi-skilled workers could assemble them following standardized procedures. Quality control was rigorous, with each bombsight tested extensively before installation in aircraft. Japanese industry, at peak production, might produce 50 Type 1 Model 2 bombsights monthly, and even that figure assumed no material shortages or production disruptions from air raids. Each Japanese bombsight required extensive hand-fitting by skilled technicians, a bottleneck that couldn't be eliminated given available manufacturing equipment. Major Kenji Yamamoto, who had worked closely with Shibata throughout the evaluation, presented data on bombardier training effectiveness. Based on captured American training records and combat reports, American bombardiers using Norden bombsights achieved circular error probable of approximately 370 meters from 6,400 meters altitude under combat conditions. Japanese bombardiers using conventional sights achieved CEP of approximately 800 meters from the same altitude. The American advantage was more than 2-to-1, and that gap widened at higher altitudes where Japanese bomb sights became increasingly inaccurate while Norden performance remained consistent. But these figures assume clear weather and no combat interference, Yamamoto cautioned. Under actual combat conditions over heavily defended targets, American accuracy often degraded significantly. Cloud cover, anti-aircraft fire, fighter attacks, and equipment failures all reduced real-world performance below test conditions. This observation provided cold comfort. Even degraded American bombing accuracy exceeded Japanese capabilities. And American doctrine emphasized overwhelming force, sending hundreds of bombers against single targets to ensure destruction, even with moderate accuracy. Japan couldn't field hundreds of bombers, couldn't sustain the losses such campaigns would entail, and couldn't match the bomb tonnage American industry produced. The discussion turned to defensive implications. If Japan couldn't match American bombing technology, perhaps it could develop countermeasures. Improved fighter interceptors, better anti-aircraft systems, dispersed manufacturing to reduce target concentration, hardened facilities to withstand bombing damage. Colonel Masahiro Tanaka, responsible for air defense planning, outlined the challenges. American bombers will approach at altitudes exceeding 8,000 meters, speeds over 400 kilometers per hour, in formations of hundreds of aircraft. Each bomber carries 10 to 12 defensive machine guns. Fighter escorts will accompany them, likely using the same long-range capabilities their bombers possess. Our interceptors must climb quickly, reach extreme altitudes, sustain combat at those altitudes, and somehow survive attacks from fighter escorts and bomber defensive fire. He paused, letting the magnitude of the problem sink in. Our best interceptors, the Mitsubishi A6M0, excel at low to medium altitude combat but struggle above 7,000 meters. Our Army's Nakajima Ki-43 has similar limitations. We are developing high-altitude interceptors, but these programs require years, resources we don't have, and will produce limited numbers. The anti-aircraft situation was equally problematic. Japanese heavy anti-aircraft guns could reach 8,000 meters, but fire control systems lacked the precision required for effective engagement. American bombers would attack in formation, spreading across several kilometers of sky, requiring coordinated fire from multiple gun batteries. Japan's fire control technology, primitive compared to American systems, couldn't achieve the coordination necessary for effective defense. We are attempting to defend against 21st century warfare using 19th century methods, Tanaka concluded grimly. No amount of courage or determination can overcome this technological disparity. The meeting extended through the afternoon and into evening, as engineers and officers grappled with strategic implications. The captured Norden bombsight had provided a window into American capabilities, but that window revealed a vista Japan couldn't reach. American industrial might, technological sophistication, and systematic approach to warfare created advantages that Japanese spirit and sacrifice couldn't counter. Takeuchi summarized the consensus in his report to the Supreme War Council. Examination of captured American bombing technology reveals systematic American superiority across multiple domains: equipment quality, manufacturing capability, training effectiveness, and strategic doctrine. Japan cannot achieve parity in any of these domains within the timeframe relevant to current conflict. Defensive preparations must assume American bombing capability will systematically dismantle Japanese industrial capacity, beginning in late 1944 or early 1945. The report was received in May 1943 and promptly classified at the highest secrecy level. Conclusions were too damaging to morale, too defeatist for a military culture that emphasized willpower and fighting spirit over material factors. A few senior officers read it carefully and understood its implications. Most preferred to believe that Japanese determination would somehow overcome American advantages. June 1943 brought the beginning of Japan's experience with American strategic bombing. While not yet targeting the home islands, American raids against Japanese-occupied territories demonstrated the pattern that would eventually devastate Japan's cities. Formations of B-24 liberators struck Rabaul, each bomber releasing its payload with precision that Japanese forces couldn't match. Lieutenant Commander Shibata, now serving as technical advisor to Air Defense Headquarters, watched reports flow in from Rabaul. The American bombing accuracy wasn't perfect. Many bombs missed their targets, some by wide margins, but enough hit to systematically destroy airfields, supply dumps, and port facilities, and the Americans kept coming, day after day, replacing losses faster than Japan could inflict them. They are conducting industrial warfare, Shibata told his staff. Each bombing raid is a factory operation. Standardized procedures, interchangeable crews, mass-produced equipment, systematic destruction of target lists. We are conducting artisanal warfare, small groups of elite pilots and crews achieving individual brilliance, but lacking the capacity for sustained campaigns. Industrial warfare defeats artisanal warfare, always. By late 1943, American submarine warfare had effectively severed Japan's maritime supply lines. Raw materials, food, fuel, everything Japan's war economy required became increasingly scarce. The precision instrument industry, already struggling to produce Type 1 Model 2 bombsights in minimal quantities, faced impossible material shortages. Chrome for hardening steel components unavailable. Optical, glass blanks for lenses, sporadic supply at best. Precision bearings for gyroscopes manufacturers prioritized aircraft engines and other critical systems. The bombsight program, always marginal, became unsustainable. In December 1943, Shibata received orders to shut down Type 1 Model 2 production and redirect the engineering team to more critical projects. The few bombsights already produced would equip elite units, but no further manufacture would occur. Japan's attempt to replicate American bombing technology had ended in quiet failure. Shibata visited the Technical Research Institute one final time before reassignment. The captured Norden bombsight remained where it had been since 1942, now covered with a canvas tarp to protect from dust. He pulled back the covering and studied the device that had consumed 18 months of his professional life. The irony struck him forcefully. This single bombsight, representing perhaps $13,000 of American production cost, had cost Japan over $2 million in development expenses, thousands of engineering hours, and scarce materials that could have supported other programs. And for all that investment, Japan had achieved nothing approaching the original's capability. "We spent more trying to copy it than the Americans spent developing it," Shibata said to Yamamoto, who had accompanied him. "They invested in a complete bombing system technology, training, doctrine, industrial capacity. We invested in attempting to copy a single component of that system, ignoring everything else. The failure was inevitable from the start." Yamamoto nodded slowly. "Do you believe our leaders understood this, or did they genuinely believe we could match American capabilities?" Shibata considered the question carefully before answering. "Some understood. General Takeuchi understood from the beginning. But understanding and accepting are different things. To accept that we cannot compete technologically is to accept that we cannot win the war. That acceptance requires courage our military culture doesn't cultivate." January 1944 brought the first of what would become routine American air raids against Japanese-controlled territories. The pattern was now established and relentless. Formations of heavy bombers, each equipped with Norden bombsights, systematically destroying military and industrial targets. Japanese defenses inflicted losses, sometimes severe, but American production replaced losses faster than combat-consumed aircraft. By June 1944, American forces had captured Saipan, Tinian, and Guam Islands within B-29 superfortress range of the Japanese home islands. The strategic bombing campaign against Japan itself would begin soon, bringing Carl Norden's bombsight to the target it had been designed to strike, distant industrial centers requiring precision destruction. The first B-29 raid against Tokyo occurred on November 24, 1944. Lieutenant Commander Shibata, now serving in Tokyo's Air Defense Headquarters, watched the radar returns as American bombers approached at altitudes exceeding 9,000 meters. Japanese interceptors struggled to reach that altitude, and those that did found the B-29's speed and defensive armament nearly impossible to overcome. The bombing accuracy varied widely. Some formations achieved excellent results, placing bombs precisely on target factories and warehouses. Others scattered bombs across wide areas, missing their intended targets by hundreds of meters. Weather, combat damage, equipment malfunctions, and crew fatigue all degraded performance below peacetime test standards. But the cumulative effect was devastating. Month after month, American bombers returned, each raid destroying more of Japan's industrial capacity. By early 1945, the strategic bombing campaign had transitioned from precision attacks on specific targets to area bombardment of entire cities, incinerating urban areas with incendiary bombs that required no precision guidance. The Norden bombsight, designed for precision destruction of specific industrial targets, now guided bombs that would ignite firestorms, consuming square kilometers of wooden Japanese cities. The terrible irony wasn't lost on Shibata. American technology, designed to minimize civilian casualties through precision, now facilitated their destruction through area bombardment. March 1945 marked 3 years since the captured Norden bombsight arrived in Tokyo. During those 3 years, American bombers had systematically destroyed Japan's ability to wage war. The factories that might have produced bomb sites were now rubble. The engineers who might have solved technical problems were dead, drafted into service, or scattered across the Pacific, defending territory that couldn't be held. The materials that might have enabled production were at the bottom of the ocean, victims of submarine warfare. General Takeuchi, who had supervised the original Norden examination, requested one final visit to see the captured bombsight before his expected reassignment to Manchuria. Shibata accompanied him to the Technical Research Institute, now largely abandoned as personnel were redirected to more urgent wartime needs. The bombsight remained under its canvas covering, untouched since Shibata's last visit. Takeuchi pulled back the tarp and studied the device silently for several minutes before speaking. "We learned the wrong lesson," he said finally. "We saw this device and believed the lesson was about technology that we needed to replicate American equipment to achieve American results. The real lesson was about systems. The Americans built a complete system. Industrial capacity to mass-produce precision instruments, training programs to develop skilled operators, doctrine that employed the technology effectively, and strategic vision that understood what a bombardment could accomplish." He paused, choosing his words carefully. "Japan has attempted to wage 20th century war using Meiji-era assumptions about combat. We believed spirit and sacrifice could overcome material disadvantages. This device," he gestured at the Norden, "proves that belief false. Wars are won in factories and training schools as much as battlefields. The Americans understood this. We did not." Shibata had reached similar conclusions months earlier, but hearing them articulated by someone of Takeuchi's rank and experience provided validation. "Do you believe this understanding will survive the war? Will future Japanese military leaders remember what we learned examining this bombsight?" Takeuchi smiled sadly. "I doubt the institution will remember. Institutions rarely do, but individuals will remember. You will remember. I will remember, if I survive. And perhaps someday, when emotions have cooled and honest analysis becomes possible, someone will study what happened and understand why." August 6, 1945. The B-29 Enola Gay, carrying a specially modified Norden bombsight, released an atomic bomb over Hiroshima. The bombardier, Major Thomas Ferriby, used his Norden to aim at the Ioi Bridge, achieving accuracy within 200 meters of the intended aim point, despite the unprecedented nature of the weapon. 3 days later, another B-29 using a Norden bombsight dropped a second atomic bomb on Nagasaki. The war ended days later, Japan surrendering unconditionally to forces that had achieved victory through systematic application of industrial and technological superiority. Lieutenant Commander Shibata survived the war and spent the occupation period working with American technical teams documenting Japanese military technology. He showed American engineers the captured Norden bombsight, explaining the 3-year effort to reverse engineer and replicate it. The Americans were fascinated by the Japanese attempt, examining the Type 1 Model 2 bombsights produced during the program. "You almost got it right," one American engineer told Shibata after examining a Japanese-built bombsight. "The basic principles are sound, and some of your simplifications actually improved maintainability, but you lacked the manufacturing precision to make it work reliably. That wasn't a failure of engineering, it was a limitation of your industrial base." The comment captured the essential truth Shibata had recognized years earlier. Japan's engineers were every bit as capable as their American counterparts. Japanese precision craftsmanship was renowned worldwide, but individual skill couldn't compensate for systematic industrial limitations. American factories possessed machine tools Japan lacked, materials Japan couldn't access, and production capacity Japan couldn't match. The captured Norden bombsight survived the war and eventually made its way to Japan's National Science Museum, where it remains on display as of this writing. The museum label describes it as American Norden bombsight, captured 1942, examined by Imperial Japanese Army Technical Research Institute. The label doesn't mention the failed reverse engineering program or the strategic implications of that failure. General Takeuchi survived the war and wrote extensively in his later years about the systematic factors that determined Japan's defeat. His analysis, published in 1958, drew heavily on lessons learned examining the captured Norden bombsight. The book emphasized that technological warfare required comprehensive industrial and educational systems that couldn't be improvised during wartime. "We examined the Norden, expecting to find a secret weapon," Takeuchi wrote. "We found instead a manifestation of American systematic thinking, careful development, extensive testing, mass production, comprehensive training, and realistic doctrine. The bombsight was merely the visible expression of invisible advantages. We could copy the device but not the system that produced it. That asymmetry doomed us." Post-war interviews with American veterans of the strategic bombing campaign revealed their own perspectives. Bombardiers who had used Norden bombsights in combat universally praised the device's capabilities, but acknowledged its limitations. Under ideal conditions, clear weather, no combat damage, experienced crews, proper maintenance, the Norden achieved remarkable accuracy. Combat conditions were rarely ideal. Cloud cover obscured targets. Anti-aircraft fire disrupted bombing runs. Fighter attacks forced evasive maneuvers. Equipment failures occurred at critical moments. Crew fatigue degraded performance. The average circular error probable in European combat was approximately 370 meters, far worse than the 75-foot performance achieved in peacetime testing. But even that degraded performance exceeded what any other nation achieved during World War II. German bombsights, despite technical sophistication, lacked the Norden's integration with autopilot systems. British bombsights, optimized for night bombing, sacrificed precision for ease of use in darkness. Japanese bombsights, handicapped by manufacturing limitations, never approached acceptable accuracy. The strategic implications extended beyond World War II. American bombardment doctrine, refined through experience with Norden-equipped aircraft, influenced Cold War nuclear strategy. Precision bombing concepts developed in the 1940s evolved into precision strike capabilities using laser-guided and GPS-guided weapons. The systematic approach to warfare that produced the Norden became foundational to American military thinking for decades. For Japan, the lessons learned examining the captured Norden influenced post-war industrial development. Japanese industry rebuilt with explicit focus on precision manufacturing, quality control systems, and systematic approaches to production. The transformation from the primitive manufacturing base of 1945 to the sophisticated industrial powerhouse of the 1980s reflected, in part, lessons learned from technological defeat. The story of Japan's captured Norden bombsight transcends simple technical analysis. It illuminates fundamental questions about technology, warfare, and industrial capability. Superior individual engineering skill cannot overcome systematic industrial limitations. Copying visible technology without replicating supporting systems produces failure. Wars are ultimately won by societies, not by weapons. Carl Norden, who designed the Bombsight in the late 1920s and early 1930s, reportedly never fully appreciated the strategic significance of his creation. He saw himself as a designer of precision instruments, not an architect of military victory. The device was simply an engineering solution to a technical problem: how to deliver bombs accurately from high-altitude aircraft. But that technical solution became a strategic weapon, enabling American forces to systematically dismantle enemy industrial capacity from beyond effective retaliation range. The psychological impact of precision bombardment, the certainty that critical facilities would be destroyed, that losses would be replaced faster than combat consumed them, that no defense could prevent eventual annihilation contributed as much to Allied victory as the physical destruction the bombs inflicted. Lieutenant Commander Takeo Shibata, the Japanese engineer who first examined the captured Norden in March 1942, lived until 1989. In his final years, he occasionally lectured at technical universities about the wartime reverse engineering effort. His talks emphasized the importance of systematic thinking over individual brilliance, comprehensive preparation over improvisation, and honest assessment of capability limitations. "We faced an opponent who had spent 15 years and $1 billion developing a bombing system," he would tell students. "We attempted to replicate it in 18 months with a tiny fraction of their resources. The failure was predetermined." The valuable lesson wasn't about bomb sites. It was about understanding what you can and cannot achieve, given your actual capabilities rather than aspirations. When asked if Japan could have won the war with better technology, Shibata's answer was consistent. No, technology mattered, but industrial capacity, resource access, and strategic depth mattered more. America could lose 1,000 bombers and replace them in months. Japan could lose 50 aircraft and never replace them. That arithmetic determined outcomes far more than any specific technology. The captured Norden bombsight remains on display in Tokyo, a monument to American engineering achievement and Japanese industrial limitation. Visitors photograph it, read the descriptive label, and generally move on to more dramatic exhibits. Few understand that this 50-pound mechanical computer represents one of the pivotal technologies of World War II, or that Japan's inability to replicate it illuminated systematic disadvantages that would ultimately determine the war's outcome. In the final analysis, the story is not really about a bombsight at all. It is about the collision between two industrial philosophies, two approaches to warfare, two visions of how technology and organization combine to achieve strategic objectives. America built systems, Japan built devices. Systems defeated devices. The lesson, for those willing to learn it, transcends the specific historical moment and speaks to timeless principles about preparation, capability, and honest self-assessment. The Norden bombsight enabled America to conduct systematic strategic bombardment, destroying enemy industrial capacity faster than it could be regenerated, forcing capitulation through relentless material pressure rather than climactic battles. Japan's examination of a captured example revealed this truth in stark detail. Wars of industrial attrition are won by superior systems, and systems cannot be improvised by even the most talented individuals. That understanding came too late to change Japan's fate. But it survived the war, preserved in technical reports, personal memoirs, and institutional memory. The captured Norden bombsight taught Japan a lesson about systematic thinking that would shape its post-war reconstruction and eventual emergence as an industrial and technological powerhouse. The irony is profound. Defeat by American systematic superiority ultimately taught Japan to think systematically, transforming vulnerability into strength across the decades following surrender. The device sits today in its museum case, silent testimony to the power of comprehensive preparation, systematic development, and honest recognition of capabilities and limitations. Engineers and historians study it, understanding that this assemblage of gears and gyroscopes represents far more than precision bombing technology. It represents a philosophy of warfare that Japan faced, failed to counter, and eventually adopted in peacetime pursuits. Thank you for watching. For more detailed historical breakdowns, Check out the other videos on your screen now and don't forget to subscribe.